Good day, everyone. Thank you for attending this presentation on the autocorrelation function, weekly station processes, and autoregressive models. Today, we will explore this essential time series concepts using relatable analogies and practical examples. Let's begin with the concept of autocorrelation. In time series analysis, autocorrelation measures how much a current value depends on its previous value. One way to grasp this is by comparing it to weather behavior. Imagine you're keeping track of temperatures over several days, like how today's weather may be influenced tomorrow's. Autocorrelations describes a similar relationship between past and present values in a time series. Here is a graph of UK temperatures over the last 100 days. Each data point represents the daily temperatures. Notice how consecutive days' temperatures are similar, which reflects autocorrelations in the time series. Think of each day's temperature as influenced by the previous day. If today is warm, tomorrow will likely to be warm. Although they are not necessarily identical, if today is cold, tomorrow may be also cold. This influence is similar to how autocorrelation functions in time series. Now, let's look at a different type of autocorrelations. High autocorrelation means today's value strongly predicts tomorrow's, like stable temperatures. Lower autocorrelation means a weak predictions, like variable climates. No autocorrelation implies no connection between today's and tomorrow's values, similar to random weather patterns. Autocorrelations also occurs at different lags. For example, lag 1 autocorrelation asks how much does today weather affects tomorrow weather. Lag 2 asks how much does today weather affect the weather 2 days from now. The influence weakens over time, but there's still a connection. So what's the key takeaway then? Autocorrelation can be considered the memory of a time series. High autocorrelation reflects a strong influence from past values, much like a string of similar weather dates. Low autocorrelation indicates weaker influence, while no autocorrelation suggests no predictability from past data. Now, let's talk about some characteristics of time series data. Now, a time series is weakly stationary if it meets 3 criteria: constant mean, constant variance, and constant covariance, depending on only the lag. The stability over time is crucial for many time series models. The autocorrelation function ACF measures how past value influence future values at different lags. This equation defines the ACF for a weakly stationary series, showing how the covariance at lag h related to the variance. In mathematical notations, as we've seen on the screen, for a weakly stationary series, rho h equal to covariance between xt and xt minus h. H here represents lag h and over variance xt. Next, we're looking at AR1 model given by xt equal to constant delta plus phi1 times xt minus 1, which is the past value of xt plus wt. Wt are independently and normally distributed errors with a constant mean equal to 0 and a constant variance sigma square w. We also have 2 more assumptions regarding about this series. Errors wt are independent of xt. The series xt is weakly stationary if phi1 is less than 1. We also want to look at the 3 important key properties regarding the AR1 process. First, we're looking at the mean. Expect the value of xt equal to mu, which is equal to delta over 1 minus phi1. This formula gives the expected or average value of the AR process. The mean depends on the constant delta and the autocorrelative parameter phi1. If phi1 is close to 1, the process has strong memory effect, meaning past values significantly influence future values. Variance xt, which is equal to sigma square w over 1 minus phi1 square. The variance measures how much the values fluctuate around the mean. It depends on the noise variance sigma square W and the parameter find one. Find value close to 1 leads to greater viability in the series. Correlation function ACF, rho H equal to find one H, means that the correlation function describes how the correlation between two value H periods apart decays over time. So the influence of the past value on the current ones diminishes exponentially as the lag H values increases. Now we're looking at the journal form of AR1 model. The ARH model generalizes the AR1 model to a higher lags. Here, today's value depending on the previous H values. These models is useful when more distant past value has a significant influence. Now, finally, we're going to look at the deviations of AR1 properties. Here is the detailed deviation of the mean variance autocorrelations functions of the AR1 model. This equation are fundamental to understand how the AR1 model work. We have the same assumption settings when we derive an AR1 model. First, we're looking at the mean. The AR1 model is xt equal to constant delta plus find 1 times xt minus 1 plus wt, where wt is a noise term, a white noise term with a mean 0 and constant variance. To derive the mean, take the expected value of them on both sides of the equation. Since the expected value of wt equal to 0 and delta is a constant, then the expected value of xt equal to delta plus find 1 times expected value of xt minus 1. Assuming this stationarity, expected value of xt equal to expected value of xt minus 1, which is equal to mu. So mu can be represented by delta plus find 1 mu. We group the like term together, make mu as a subject, then mu can be expressed by delta over 1 minus mu 1. Again, the absolute value of a find 1, which is almost less than 1. Variance of AR1 process. The variance to obtain this value, first we're going to square the both sides and take the expected value of the equation. The variance of xt equal to find square 1 times variance xt minus 1 plus variance wt. Due to stationarity, variance xt equal to variance of xt minus 1, which is equal to sigma square x. Then sigma square x equal to sigma square 1 times sigma square x plus sigma square w. Solving the value of sigma square x, then we can express it by functions of x square w over 1 minus find 1 square. Again, the absolute value of find 1 must be less than 1. Autocorrelation functions of AR process. For one period apart, a gamma 1 equal to expected value of the multiplication of xt and xt plus 1. Then this equation also equal to find 1 time variance of xt. And rho 1 equal to find 1, which already defined before. For h time periods apart, gamma h equal to find 1 time gamma h minus 1, and gamma h also equal to find 1 square times gamma h minus 2. If we keep using the same process, repeating again and again, then eventually gamma h can be expressed by find 1 to the power h times gamma 1, where also equal to rho h times gamma 1. So from this final expressions, we know that the autocorrelation decays exponentially as h increases and the absolute value of find 1 less than 0, indicating that the influence of past values diminishes over time. In conclusion, autocorrelations measures how past value in a time series influence future ones. The AR model helps us formalize these relationships, make them useful for forecasting and analyzing our data. Thank you for your attention.